Good evening and welcome to TI Office Hours. I'm here with my good buddy, Tom Reardon. My name is Curtis Brown from Texas Instruments, and I'm happy to be able to be doing this with you this evening. I just want to express one more time that, I'm sorry we're all in this situation, and I know it's tough. Many of you have been teaching for a long period of time, trying to get ready for your students in this kind of strange period of dealing with teaching at home. But we are, at TI we hear you, and we're trying to do what we can to help you out. And so we're bringing along experts to do some things with you. And tonight we've got Tom Reardon. We're going to do some geometry explorations. Tom, thank you for joining us. I'm going to have you go ahead and take it away right from here.
Okay, well, hello, everybody. Special shout out to Jack and Logan and Luke and Eve and Karen Pete. Special shout out to them. Since you mentioned about these crazy days, there was a tweet that went out today that I'm going to share to start it off, if that's okay. Teachers wrote out, "I'm working twice as much to deliver 2/5 of the content at 50% effectiveness to 2/3 of my students, and have had only time to do like 10% of my 5-year-old's learning." Now, I thought for sure that was a math teacher that said it. It was a social studies teacher said it, but I loved all the fractions.
Oh, wow.
And so on. I thought that was great. I said, well, just from a math teachers, no, social studies. So anyway, we sense your pain, and we, do whatever we can do to help you. So we're going to be looking at geometry, so I can go ahead and get started. Is that right?
You can
Okay.
share your screen.
All right. All right, so we're going to start looking at transformational geometry first. We have lots of other things we're going to be sharing with you, but transformational geometry I thought would be a good way to start. There are 4 of them. This one is reflections, and I'll go through the 5 on this one. TI software, we'll be using tonight. And the second slide is just shows several different reflections, red and blue, kind of get a feel for what's going on there, and a line of reflection. And this one's a picture taken from, actually it's Half School in Connecticut, just to set up the idea about having reflections. But here's where all the fun happens, right here. This is where the math happens. And so what I want to do is reflect triangle ABC about this pink dotted line here. And this is the icon that does that. And when I reflect it, I get the image, and the blue is the pre-image. And what we'd like to do is make it interactive. And so I'm going to grab point C and pull it. And as I do it, you can see that the other points react similarly. I can put them here. I can put the same line on the line of reflection. And this is where students can play, investigate, explore, and discover the math. So Curtis, how are you doing so far?
You're good.
We're good. We're good. Okay.
Yep.
So again, somebody might say, where's the grid? Where's the grid? And we were told you don't use the grid right away, but we will get to it. We also would like to have a different line of reflection. So I changed it to a vertical line, and now we can go ahead and investigate that. And I'm hoping students are realizing things like mirror image and so on, clones, copies, those types of words are showing up. And then finally, we can go with a diagonal slanted line, and we can see what we mean by mirror image and so on. Now, one of the things that I would want my students to be able to do is to be able to do this by hand. So I'm going to go ahead and change the template to something called connected segments. And now when I reflect this about the horizontal line, you'll notice I'm getting these dotted segments connecting A prime and A, B prime and B, and C prime and C. And Curtis, I know you already know this stuff, but what is it I'm hoping they'll notice about points S, T, and U?
Well, it appears to me that they look like they're midpoints of those segments. Mm-hmm. So I'm hoping students probably will notice that, mm-hmm. And maybe have some ideas, maybe some questions about if they can change that by moving the triangle all over the place. So I'm guessing that's probably what students will come up with. But Tom, I don't know if that's what you were looking for.
Yep, that's kind of what I was hoping for. I'm also hoping they'll realize that these dotted black lines are perpendicular to the line of reflection too. And I didn't ask you
Sure.
about that, but I was hoping that. So going on to the second template, I'm going to go to something called this. These are pre-made here. And so now when I set this up and I reflect it again, you'll notice I'm getting those dotted segments, but it's also showing me what you thought was true. And now I can go ahead and play and try it out with all different types of triangles. I don't have to just try it with one triangle, and I can move it all around, as you said, and even try it with a different line of reflection. And how does that look? So, and then we talked about the perpendicular thing. Here's where it's telling me triangle ASU is 90, BTU is 90, CUT is 90. And no matter what, those lines are perpendicular no matter what. So you make the conjecture, and now you have a pretty good idea of why it's true. Good?
Well, that's good.
Okay. So let's go ahead and bring in, oh, you know what? There's one other thing. We can also, I thought this was kind of cool, the guys who made this movable line. You can actually, instead of changing just the triangle, you can actually change the line and move the line. So notice I can grab point P, and instead of rotating the triangle, rotate the line of reflection and kind of see what's going on there.
That's really cool. Hey, Tom, I've got a question. I've got a question actually for some of our viewers, and that is, I know you said at the very beginning about that you were told, and that we've been kind of told about teaching this way and starting with just a blank sheet of paper instead of the grid to kind of guide. I'm just curious if there's anybody out there that's doing that way, so that when they introduce this to their students, this transformational geometry idea, whether it's reflections or if it's translations, dilations, rotations, whatever, if they do it without the grid first before their students have to try to worry about coordinate points.
And I hope they are, because that's what I'm hearing from the experts, okay, which I was not one until I started doing a lot of this. But now bringing in the coordinates, I'm going to go ahead and reflect about the x-axis. I can talk about it that way because we now have a grid to refer to that. And so when I reflect it, you'll notice there's going to be some kind of pattern going along with these corresponding coordinates. And we want to do is see if this is always going to be the case, no matter where we are. And then we want students to be able to make some kind of conjecture about it. And it looks like the x coordinates staying the same and the y coordinates are opposites. And instead of me telling students that's the way it is, I'm hoping they'll discover that by playing with this.
Yeah. I can see where having the grid and the coordinate points and dealing with the distance from C to that line of reflection on this grid might be a little more intimidating than dealing with it, say, on a blank sheet of paper. So I can see what those experts that you've been talking to are saying. I can understand that for sure.
Good. And again, now I'm going about the line y equals x, and you can see there's definitely a pattern here. And we in the materials that go with this, we'd say something like xy maps to y comma x. And
that's cool.
So just let them play around with that. Other things that we could talk about are areas and perimeters, slopes of corresponding sides, and so on. But I think that's a good enough start for reflections. So translations is another biggie. This one we will start with coordinates, just to go in the middle of it here. And so if I wanted to just, let's say, translate down 4 units, and then I'll press the translation button, what happened to the coordinates here? And you can see that the x coordinates stayed the same, but the y coordinates are 4 less than they were before. And again, play, grab, and so on.
Hey, Tom, there's kind of an interesting thing here that strikes me. I see you've got that arrow pointing down.
Mm-hmm.
That almost looks like looks a little bit like a vector. Like maybe I could pick that up and put it on top of each of those coordinates to show students what's actually happened to each of those coordinates. Like, could I move that?
Because we do have a translation mode called vector. So I'm going to bring in the vector. And you'll notice this vector right now is the vector 3, 3, meaning where the endpoint is. You'll notice the other endpoints at the origin. So I'm going to translate this. Let me make it so it's maybe 2,3, and I'll translate along that vector. And you'll notice the x coordinates each increase by 2 and the y coordinates increase by 3. But what you were saying before is, how about if I grab and show that each point is actually moving along that vector? That's what you were hoping for, and that's what we're able to do as well.
Exactly what I was looking for. I just thought that was, I think that's kind of an interesting piece. And I don't know if anybody out there is, has the ability to do that kind of thing, but that's kind of a neat way to play with this and see those translations happen.
Right. And also another thing I could do, I can also add to it the component vectors with it. And now you'll see I'm going over 2 up 3, and there's my resultant vector, and I can see how we're actually moving as well. So
that's really cool.
I'll turn those back off because it's easily done. But the other thing is I can now translate by moving the vector's endpoint. So what do we mean by moving directly this direction or directly this direction or going in this direction? And investigate that. So you can go by vector, or you can go by not by vector, just go up and down. In fact, let me change that back to directional. So here, go ahead.
No, go ahead. Go ahead.
So I'm just going to move this up O and over some and translate that direction. And notice it's giving me slopes of corresponding sides like AA prime, BB prime, CC prime, okay? Those are those, I'm not sides of the connected segments. So if I grab this, notice that no matter what, those are the same slopes. They're all which means that they would be parallel to each other. Kind of gives you that 3D kind of looks, so to speak. I could also look at slopes of AA prime, B prime, so on. And again, I can move the whole thing around, change it, and so on. I'm also getting the lengths. AA prime, BB prime, and CC prime are the same. They would be the same distance apart, as they should be. All right, so let's, several things I want to show. I'd love to show more on translations, but I'm going to go to what I think is the toughest one, and that is rotations. And for this one here, I'm going to rotate triangle ABC about point P through an angle of 45 degrees. So I'm going to go ahead and press on that one time. And it rotated 45 degrees. And then I could do it again for a total of 90. But from the last image, it was 45 and so on. And notice it's showing the last ghosted image. And one of the things that we could do is I could reset it, and I could ask it to show historical images. And so for this one, when I rotate 45 and another 45 and another 45, I can kind of get a feel of how it got there.
I've got a question now for our audience actually on that. Now that you've shown those historical images, when I taught geometry and we did these rotations, my traditional thing was patty paper. It would have been very difficult for me to get those out there. Does anybody else have a strategy? Do you guys do this kind of historical image thing out there that maybe this is helpful for you, or that you're seeing something different than maybe what you've seen before?
Okay, so while they're coming up with their answers, I'm going to just throw out another idea similar to that. What I want my students to be able to do, even though we're using technology, is to be able to do this by hand. And like you said, with patty paper, okay? And so I have this little thing that we put in here, and I'll click on the first drop-down menu, and you'll notice it's showing me arcs from the corresponding vertices, okay? And that kind of gave me a little bit of a hint. But then I went into the second one, and notice it's showing the students that those vertices are traveling along concentric circles. And I'm not sure they realize that, okay? And then I go ahead and do the third one, and it's showing that the arcs are also traveling along those concentric circles.
Now that's way cool. And I didn't realize that till you showed me this picture. I that just wasn't something that ever went through my mind, thinking about the fact that I had 3 concentric circles, one for each of those vertices. I don't know whether people show that to their students, or if that's a method by which they do some of these reflections, rotations. But I think that's kind of a cool one.
And what I've found, I'm glad to hear that too. I mean, what I've found is after students have done this for about 45 seconds, I'll say, do you have any idea now how to do this? And they'll say, well, give me a protractor and a compass. I think I got an idea. Actually, unfortunately, they'd say, give me that circle maker and that angle measure thing. But, you know, I get it. I get it. So again, I could be doing this with coordinates and so on, but I want to show some whole bunch of other things. So we'll move on to dilations, which is, I think, the second hardest one. So what I wanted to do here, I wanted to look at areas and perimeters of this. So I'm going to look at all the scale factors we can use, by the way. Scale factor of 3. And so I'm going to dilate this triangle about point P with a scale factor of 3. And let me zoom out a little bit so I can see it better. And you can see something's going on here with the perimeters, okay? And I can go ahead and grab this and pull it and, ooh, oh, look at that one. I can see that the perimeters are what? 3 times bigger.
3 times.
Happens to be our scale factor, okay? Now, what about area? What about area of these things? Let's go ahead and look at the areas of these. And looks like it's a lot bigger than 3 times. So let me kind of play around with this until I can maybe get some nice numbers that maybe end in 10 so that I could see what this is. And once you know it, I try to do this live, I can't get the 10s. There we go. And so what's the relationship here? When the scale factor is 3, they're what? 9 times bigger.
Ooh, yeah, 9 times.
So if in case you're not seeing that, here what we have is we have the perimeters being measured and doing the division for us. And as we change the perimeters, the ratios of the perimeters turns out to be 3. And when we do the areas, the ratios of the areas seems to be 9. And
that's
so,
really kind of a neat thing. I really like that.
well, me too. I'm glad to hear that. Okay. And then if you still don't get it, this will hit you over the head and say the scale factor was 3 and the scale factor squared was 9. And what we're hoping to do is if we change this to 2 or a half or whatever, what would happen? And you're always going to be the ratio of the perimeters is the scale factor. The ratio of the areas is the scale factor squared. But again, we'd have to do a lot more things than just scale factor 3.
For sure. Hey, Tom, I do have a question for you.
Good.
Okay, you've kind of gone through these 4 transformational geometry ideas: reflections, translations, rotations, dilations. It seems like they all look the same. Are the investigations kind of the same ideas in each one of these? I'll look at the connected segments. I'll look at the perimeters and areas. I'll look at the slopes of the sides. Kind of begin to make up all of those conjectures that I would expect to do in my geometry class.
Yeah, there are lots of them. I mean, if you look at here, if we look at the pre-made templates, like if we want to talk about corresponding angles and sides, what's happening, perimeters and areas we just did, slopes of sides, distance from the P to the vertices, grid and coordinates. Okay, all these things will be investigated. So yes, okay. They're different for each one because each one has different things about it.
Well, this is cool.
So I got to show you one more thing though. The scale factor of 1. I never saw this until I got this software. I have no idea what this was going to be. So I'm going to dilate this triangle about P of scale factor -1.
Hold on, wait. Let me think about it.
Okay. All right, ready?
I think I know what's going to happen.
Okay. Oops.
If I make a conjecture, I was just going to say, if I make a conjecture, will you forgive me? Okay. I was right, but that's really cool.
Yeah, it's a rotation of 180 degrees.
Yeah.
And, and if I go scale factor -0.5, look what happens. It's still a rotation, but now it's half the size.
Right.
So anyway, so these have all been put together in one spot on TI's website. So I'm going to go to TI's website right now. And
that actually, man, okay, so that actually gives some real life. Okay, this is going to be a discovery recorded on YouTube forever. That gives some real life to polar coordinates, and the reason why you can do negative angles in polar coordinates, and the reason why it works that way.
Yep. Yep. Nice connection. I'd give you a Pez for that. That would be a Pez. That would be Pez worthy.
Wow. Okay.
All right. So if you go to TI's website and go to geometry under their Math-Nspired, and Curtis is going to show us at the end where Math-Nspired is, and I have a link on a website that I'm going to give to you. But if you go to transformational geometry and click on reflections, what TI has put together is a series of videos and student activities and teacher notes that you can use to teach remotely, so that you can just have your students watch the videos. If they have the TI-Nspire technology, they can play with it. If not, they can just do the videos. The assessments are there, the answers are there. It's a way of trying to take that part away for you. You have to create all these things. And it's on reflections, dilations, rotations, translations are all there. So please take advantage of that if you need it. So Chris, we have any questions? Have we had any questions from anybody yet?
I haven't seen anything pop up in the question marks yet. I do want to make the comment that the link to your website is in the discussion already. We put that in the chat just now. So the link to this website, Tom, that you put together, we put that bit.ly down in the chat already. So anybody who's on here can grab that and see it.
Okay, so speaking of that, this is the website that has more information than we could cover tonight. But all the TNS files, you can get these and download them as one zip file, everything that's mentioned here in one fell swoop. Here's the transformational geometry unit right here. And on these, I have the thick ones are the links to the materials, and the thin ones are links to videos. So if I go too fast tonight, or if you want to share it with somebody else, you can see there's just 2-3 minute videos that they can get this. This one's only 1:48, and just kind of show them what the activity does. So with that, while we're here at Math-Nspired, let me go back to here. And so I got this one from middle grades math. It's called Slices. And I found this to be an excellent way to use technology, because I could not show this in my classroom before this. So here I have a rectangular prism, and I'm going to take a vertical plane and pass it through and show that when it does this, it's basically a square as it goes through there. And again, to me, that's just amazing. I can do that in such an easy time. And I'll go, horizontally, and it's that rectangle that's the base of that rectangular prism all the way through. So that one's not as tough as maybe this one. A triangular prism, if I pull this plane vertically, starts off being a segment, rectangle, 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 base of a square and back, and horizontally pulls up the same triangle all the way through. This really helped me a lot. I don't know about you, but it helped me a lot. Another one on this is volume relationships, and I love this one, but I'm only going to show one part of it, and see what I'm curious to see if anybody likes this. So if you could give me a yay or a nay at the end, I would appreciate it. So here I've got a cone, radius 1, height of 1, and the volume is 1 pi. So I'm going to go ahead and grab this and change the height to 2 and 3, and it's looking to me like the formula for the volume of a cylinder is radius times height times pi. That's my conjecture so far. But now I'll go back and I'll change the radius to 2. Oh, and that's not working anymore. It's not 2 times 1, 2 times. It looks like I have to double the 2 times 3, the 2 times 4, 2 times 5. So my first conjecture wasn't true. Try this again now with maybe a radius of 3. Oh, and now I got to multiply by 3 times 3 is 9, times 3 is 27, 12 times 3 is 30. I got to multiply by another 3. So it seems to me I have to multiply the first one by 1, by 2, by 3. The next one I'm probably going to have to multiply by another 4, and I do. And I finally put together that I've got to square this thing multiplied by the height to get it. So pi r squared h seems to be the case. And I know I did that quickly here, and students would have to take much more time to think about it, but it's just another way of doing this. See that it's the area of the circle times the height, pi r squared h. So does anybody out there like that, or am I the only one? And I will not feel bad if I'm lonely on that one.
Well, I'll join you on that. I think that's a really nice demonstration of that concept. And I like the fact that you went with a radius 1 first, just from a pedagogical standpoint, and from maybe a developmental standpoint, thinking about, we're used to computing area of figures, two-dimensional figures by multiplying the base and the height, right? That's what we do in two-dimensional figures. Or the width and the height, or the width and the length, whatever. And so it seemed reasonable to think, okay, well, if I start with a radius of 1, I can just multiply these two together and see that happening. And then you kind of developed it for me little by little, and that was nice.
Okay, but nobody's talking out there, huh? Nobody's.
I haven't seen anything. We said join the discussion, and it seemed, but it'll be good.
Okay. All right. Next,
we did get a question about the link again.
Okay.
Your website.
Okay.
Yeah, which we posted down there in the chat. It was a bit.ly, right?
Yes.
Okay.
And we'll show at the end too. So here's an activity called what's right about a triangle, and so it has a 6, 8, 10, and what you do is you pull these points down and see if you can make it into a triangle, and it is a 90-degree triangle. It's a 6, 8, 10. 36 units squared plus 64 units squared is 100 squared. So the area of this square equals the area of this square. And then you can also click and get a different one and see if that's a right triangle. And it turns out, of course, that it isn't. And play around with that a little bit. Oh, come on. There we go. And you can see it is not a right triangle and so on. But the part that I really like is this part right here. And here we have a right triangle with the blue area on one leg, green area on another one, and this kind of reddish white area here. Okay. And it says, drag me down. Okay. So watch what happens. I'm going to grab that point. And as I do that, those areas become parallelograms, each same size area parallelograms, and I'm going to drop them inside that. So the area of the green plus the area of the blue is the area of the white, as long as that's a right triangle. And I can even change where the triangle is. I can change how big the hypotenuse is, and it still seems to hold true. And I think this is just an incredible visual for students.
Hey, Tom.
And those are not sure why that's true. Here I have a square that's 6 by 6. The area is 36. When I pull this and make it a parallelogram, still the same area. They have the same base, same height. So that's why that part worked. Okay. So again, I just think this is an incredible use of technology. And I could see students visualizing this video playing in their minds when they're trying to understand Pythagoras' theorem.
So Tom, I can see, first of all, we did have some comments about that they liked the 3D volume piece, and also the slicing of those for the calculus intro. And some people are talking about this one being really, really cool. I know for me, the idea of being able to connect the areas of those squares and put them together and put that into that bigger visual of the square of the hypotenuse, that was really big for me. I think this is something that students struggle with too, right? This connection between this a squared, b squared, and c squared, and seeing that and trying to figure it out. I wonder if there are some other things that folks find their students struggle with in geometry. What are maybe their most difficult topics for students to understand? And we'll kind of watch those, and maybe hopefully in the next couple minutes, maybe we can even tackle some of those. I think you've got some good visuals coming.
Okay, good. Yes. So we've always had squares on the legs and hypotenuse of a right triangle. This is areas, measures, and right triangles. This is in the geometry, math-inspired section, and I kind of updated a little bit. So you'll notice here, I have right triangle ACB here, but instead of squares, I have equilateral triangles. And using the geometry, Nspire geometry, I was able to find the areas of those. And you can see there's a relationship here already. But is it true all the time? And that's where the dynamic geometry comes in. So I'll grab point B and make this change, be dynamic. And the area of the blue plus the area of the brown is always the area of the green, no matter what. And so I just thought that was cool that you could have something else besides squares.
Has anybody out there ever seen this before? Because this was new to me. When Tom showed this to me earlier, I about fell out of my chair.
But wait, there's more. There's more. You can also do it with semicircles. So I have the area of a semicircle, green one, blue and red one. And you'll notice that when you add them, and again, make them bigger, the area of the blue plus the area of the green is always the area of the red. And then I was watching a video NCTM did, it's got to be 25 years ago. And it was something like this. Put ducks, similar ducks on here. The area of the green duck plus the area of the pink duck on this leg is equal to the area of the blue duck on the hypotenuse. And that just stayed with me, So when I was putting this together, I made this work out. I do not have the areas of them. I did not spend the time finding the areas of these ducks, sorry, but I'm confident that it's true.
I just am. That's such a fascinating thing, and we've seen a few people have commented they've never seen this before either, and I've also seen a comment that this is really cool. So that's man. Thanks for sharing this one. This was really a cool one. I did get a question or a comment about one of the things that's most difficult for students. And that is the angles formed by parallel lines in a transversal. So Tom, do you have anything set up for that?
That was pretty good because I do have one and two. So I'll skip ahead to that one. So this one is a very quick one. Okay, it's not, and it'd be a good one, but I think what it accomplishes in a few seconds is great. So these two lines, FA and JB, are parallel, and these two corresponding angles are measured to the nearest tenth. And you can see that cut by this transversal, those corresponding angles are equal, okay? But if I grab D and move the transversal and rotate it, the corresponding angles change, but they're always equal. No matter what, they're always equal. And even if I slide the lines up and down, they're equal. So this to me is a really good way of having students not have to buy into it, say, well, they're equal. No, you can see that they're equal. You can grab them and pull them and see that they're equal. So thank you for that question, whoever it was. Was right up my alley. So I appreciate
Veronica Franklin is not a plant.
She's a person. She's not a plant. No, she may be vegetarian, but
no, she was not a plant.
Sorry,
she was not a plant in the audience by any stretch.
This is
so I do I do have one other comment. So for me, Tom, and I'll go ahead and play the plant here. I did struggle with area formulas with my students. I know we kind of teach them and make them memorize them, but making them relatable and understandable was something that I struggled with my students. It always seemed like, okay, we're gonna force you to remember this, and in particular, the area of a trapezoid. That was always the one that just seemed like, okay, well, yeah, I can kind of show you where this comes from, but I never could get a really good feel for that one.
Well, yeah, and yeah, you are playing the plant because you knew this was one we both like. And I don't know who created this, but
well, I am a plant.
But so, yes, I will definitely thank them for it. But so here's area formulas, and one of the things I want my students to understand that area means the amount of surface covered, and it's measured in square units. And it's sad that they just don't know. They just don't know what area. You ask them area, you say length times width, and that's what they think it is. So
Yeah.
So I'm going to build up to that one that you were talking about, the trapezoid. I'll start with a parallelogram and a rectangle. They have the same base, same height. They're on this little grid here, and you can count and see they have the same base, same height. And when I've done this with students, I'll say, do you think they have the same area? And almost, if they're untrained, almost all of them will say no. They'll say this one's a rectangle and this one's kind of broken. Somebody sat on and it's kind of broken. And you can also change the size of it and so on, change the height, change the base and so on.
Do a favor for me. Can you pull point P? Is that possible?
So if I take point P and pull it.
Oh, nice.
That's the part right there. And I know teachers will say, well, I have my students do that with construction paper. I'll cut off this right triangle and put it over here. And I'll say, continue to do that. That's great that they're doing that with their hands, but this is saving trees. And I can see them replaying this video in their head to see that, yes, they're the same. So the area of a parallelogram is base times height. There's no doubt. Okay.
And you can change that one. Yeah.
Even change that. I can even change
your construction paper.
That one. Okay.
Yep.
So with that, now we can go ahead and look at a triangle. So this triangle has the same base, the same height. And by the way, I'll ask students, do you think they have the same area? And I've had kids go, yeah, because you're not getting me twice in a row. I didn't, no, they don't. They don't.
I was just going to say, yeah.
Okay. All right. So now here I can go ahead and change the size and so on. But now instead of pulling Q, I'm going to make a upside down parabola. And now I've got two triangles congruent, and they make up the same area as this. So if this was base times height, triangle's half base times height. I mean, this is it. This is just as how kids can see it. Okay. And they get it.
Sure.
They get it. But going to the one you like, which is the trapezoid, I'm as a math teacher teaching geometry for 25 years, never saw this. I was told middle school teachers see this. They have the same height. They do not have the same base. They don't have the same area, right? I'm going to take that point R and I'm going to grab it and make that frown again. And now I have two trapezoids with the same area as this, right? So the area of the area of this is base 1 plus base 2, that quantity times the height. The trapezoid's got to be half the sum of the bases times the height, which is that formula
that brought new life to the area of a trapezoid for me. And I know, it might seem disingenuous because I work for TI and whatever, but I had never seen this. This was created long before I came here, and I still am shocked. That is one of the coolest ways of demonstrating the area of a trapezoid that I've ever seen. That's really fun. That's a really fun one. So Tom, we got another question, and this person might be putting you to a little bit of a challenge, but they said that trigonometry is one of the most difficult things for their students to kind of relate to. And so be thinking about that, because I know that's probably not your next example, but might be a couple on the way.
Okay, so let me get through a couple of these, and I'll cut a couple out and see if I can grab one somewhere. Okay, for trigonometry.
Fair enough.
All right, so before we do that, and I appreciate at least I know somebody's listening. I'm happy to hear that. That's always good. All right, so this one is called Tangents to a Circle, and I'm just showing 2 pages from it, though there's several good parts to it. So here we have 2 lines tangent to a circle from the same exterior point. And you can see that the length of AB and the length of CB are the same. But that's just one example, and that's not enough to make a conjecture. So I'm going to grab point B, and notice, no matter when I do this, they're the same. I can make the circle smaller or larger. I can move the circle around. And then I can even do this. And notice when I get here, it doesn't work because we don't have tangents anymore. Okay. But so my conjecture is these 2 segment lengths are the same. The concept of proof, this can kind of help students, the next page, do the proof. So in order to get these 2 segments congruent, we got to prove triangles congruent. And I don't have triangles, so I need to draw in like the radii. Well, these steps right here, you click on this slider arrow and it gives you hints. So it'll say, oh yeah, draw in those radii. And what do you know about radii? They're congruent.
Well, they got to be congruent. So it's
and they're
circle.
also what to the tangent line.
They're perpendicular.
So I click on there and it tells me that. But I don't have triangles, so I need to draw in Obi.
Yep, the shared side.
And so I got two triangles congruent by hypotenuse, leg, right triangle, hypotenuse, leg. And normally that would have been great, but my geometry teacher, Mr. Erickson, who, Curtis, you've heard me speak about him many times, used to tell me if these are congruent, that means I can put one on top of the other. They completely coincide, okay? And so we based it on faith. It was like a religion back then because you really couldn't do it.
Right.
Watch what happens when I grab point D with the technology. There it goes.
Oh, that's
definitely
nice.
That triangle is congruent to this triangle. There's no doubt that that's the case.
Okay, I've got a question for everybody out there. Does it look like that point C floated through the triangle on the backside of that, or does it come through on the front? Because I'm going to start one of those Facebook things and see what happens.
Okay. All right.
Go through the back or the front.
So let me show one more thing, and then while we're showing websites, while you're showing one website, I'm going to go sneak and try to find something on trigonometry.
Oh, okay.
But I do want to show one other thing because all of these were pre-made, and there's over 1,000 activities on Math-Nspire that Curtis will show you, and over 100 or so on geometry. So I'm going to skip ahead to what I call a create your own, which means you want to do this in your class. Your students could do this if they have TI-Nspire handhelds or the software or even the iPad app. They could do this on their own. So here I'm given 3 points. Find the point that is equidistant from each of those 3 points. So here I have 3 points. They could be anywhere. It doesn't matter where. And I'm going to go through the construction kind of quickly because I think you get it, but your students, I'd go more slowly. So I'm going to go over to tools and I'm going to go to construction and I want the perpendicular bisector. And I know you might be saying there are no segments, but I'm going to find the perpendicular bisector between these 2 points. That easy. And now what I want to do is show that something that I always said, but never could actually show students. I'm going to put a point on this perpendicular bisector, and I'm going to call it point R. And what should be true about the length from R to A and R to B? It should be the same, no matter where I put this. So I'm going to go ahead and measure that. Measure that length, R to A, put it over here, and R to B, and put it over here. And now what this is the part that gets me. Grab R, and R is definitely the same distance away from A to B, no matter where it is, even if it goes off the screen on this perpendicular bisector line. Okay. And by the way, Curtis suggested me do this because we worked on a project together where we had this, and it's a great way of showing dynamic geometry software. So I've got this one. I also want to find the equidistant from point C. So I'm going to now do the same thing, construct a perpendicular bisector from point B to point C. Again, put a point on there. And I'll call it point S for lack of a better name. Oops. Well, it's small s. I'll live with that. And then find the distance from S to B and S to C. And again, when I grab S, equidistant, anywhere along. That's what a perpendicular bisector does. So I've got all the points from A to B equidistant, B to C equidistant. Where is the one that's equidistant from all three would be where those two intersect. And so I'm going to go ahead and use the intersection point tool. Say I want the intersection of this line and this one, and I'll call that point T, and I'll find the distance between each of those. So Curtis, while I'm doing that, are we getting any reactions?
So we did have one question that I'm gonna try to answer when I start sharing my screen here in just a second, and that was during remote learning, how are students getting these activities at home? They may have downloaded the software. How can they have access to the activities? And I'm going to show that real quick as soon as you're done with this construction. By the way, this is my favorite construction, and I think it definitely struck me as something I had never thought about. Perpendicular bisectors and the whole idea that they intersected at a single point and all that. That was something I taught, right? That was what I did, but I never really thought about each of those lines as lines that were the set of all points equidistant from two of those points. I never ever had really thought about those lines as equidistant sets of equidistant points from two of those points, and finding the solution to that system of two equations really is what we've done, is kind of cool.
Yeah, and what I'm going to do, what I did was this would be like a live thing, and if you were doing it with me, you could follow it. But if you couldn't, I went back and made it cleaner. Okay, I did this a little bit cleaner. So let me just show this. And I would like people out there to notice use of color, how I'm using color to help understand this. So here I want to find the equidistant from A, B, and C on a triangle. And so P happens to be on there. And notice again that what? It's always the same distance from P to A and P to B. It's always the same, even when I move the triangle. Okay.
Sure.
Then I can go ahead and add the other one like I did before. And notice R to A, R to B, and R to C is now equal, and QB, QC, they're equal. And even if I grab point A, these numbers in pairs or triples are always equal. So this is that point, that magic point, okay? By the way, can I get point R to be inside the triangle? And for sure I can. And then Curtis pointed out, what if I did the other perpendicular bisector? If I put all three, they happen to be concurrent because that's the point that equidistance from all three. You only have to do two because that's taking care of all 3 points, but it also just shows you that, yeah, that point is the concurrent of the 3 perpendicular bisectors. And it just makes more sense to me now that I can visualize it. I used to have to do this at compass and straight edge, and it never actually worked out perfectly, you know, so this was so much nicer than that.
And the connection there that you didn't show right there at the end, which is the circle that those 3 points now sit on, having a center at that point R, is just the last step.
All right, I'll go ahead. I'll put in the circle. Okay.
No, you've got it on the last page there.
There we go. There it is. Notice that R is the center. A, B, and C are on the circle because RA, RB, and RC are all radii of the same circle. And by the way, when I say RB, I keep thinking of roast beef sandwich. And did you know that the first Arby's is about 3 miles from where I live? The very first Arby's.
No way. That's really cool.
No extra charge for that. I'm not charging you any extra money for telling you that either. Just
I appreciate that. Hey, hey Tom, while you look for a trig one, let me kind of take control. So if you stop sharing for just a second.
Yep, I did.
Cool. I'm on the education.ti.com website. So if you just go to www.education.ti.com, this is the website that you will see here. Oops. And oh, somebody told me to zoom in on my browser because my browser is way too far out. So I'll zoom in on that so it looks a little bit more like what you guys might be ready to see there. Okay, so on our website, you'll have a few of these tabs here. Really quickly, I just want to show you that you can snag this activities tab. This is probably the most important one for you. And for the person who asked about where students can go to get these activities, this is the location. So they go to www.education.ti.com, and then underneath of activities, Math Inspired is where Tom has been pulling all of those activities that he was showing you. So we have a large number of activities there for middle grades algebra, geometry, and in this case, most of you guys are probably interested in what the geometry stuff is here. And this is the screen that Tom kind of landed on earlier, showing you the selection of activities for these. And so the right triangles and trig, this is probably where Tom is going to go right now to pull his selection for an activity to show you related to trigonometry. He may go to the pre-cal one, I don't know. I also wanted to just point out, somebody mentioned that students can download software right now, and that's exactly right. In fact, if I go back to our homepage, one of our promotions right now that we have going on, we have the software online underneath of this COVID support page. So if you click either on this tab or here on download now, you can find the software here on the website. Links for teachers and students, iPad software, things for you guys to grab. We've got both 84 and Nspire software up there right now. So you can go and click and grab that stuff. Send your students here if they're looking for, maybe they weren't able to take their calculators home or things of that nature. So this should be a nice, helpful way to get there. There are a lot of other activities out here. The activity Tom mentioned about those perpendicular bisectors is actually underneath our STEM activities. You guys can go and explore. I don't want to take any more time away from Tom though. So Tom, if you're ready to share your screen, go ahead and hit share, and then I'll hit stop sharing, and we'll be ready to go back to you.
Okay. Okay. Oops. There. So I went on and I grabbed the first one I saw was sinusoidal modeling, and I've never done this one before, so I have no idea what it does. So I'm going out on a limb here, literally. So what I did find was this, and I thought this was really good. I mean, I love the fact that we have these sliders and how you can. So when I teach mathematical modeling on sinusoids, there's 4 parameters: y equals a cosine of the quantity b times the quantity x minus c plus d. And notice that I can go ahead and start increasing the amplitude a value and see immediately what happens there. I can also change b and see what happens and how it makes the period, when b decreases, the period increases. So I can get that idea out to my students. C is a phase shift. And now what I'm doing is the curve is shifting to the right or left, depending upon how you look at it. And then the D shifts it up and down. And so if I had data, I could try to actually mathematically model this. And so this is just one. I'm hoping that might be something they're talking about. If it isn't, I apologize. But if you go to Math-Inspired, like Curtis said, in the pre-calculus, there is a whole thing on trigonometry. If you're interested in modeling, I'll add to the website that I created. A teacher just asked me for mathematical modeling from Nashville, Betty Mayberry, who used to do the TQ conferences, but there. And I'll put a link there, and she's having her students do that problem remotely. I have a video that kind of talks them through it. So I'll put that on there if that's any help to that person. Okay. So with that, let me just go back to the website. This is the website I created. Again, all the TNS files, if you can right now get this software for 6 months until August 15th. So if you're viewing this later, sorry if you've gone by on this. You can use any of these TNS files. If you're teaching geometry and transformational geometry, here's a unit ready for you to teach remotely. Got everything there. And then these are all the things I talked about and many more. And if I didn't talk about them, here's videos that goes with them that kind of help you understand it. Here's that create your own that Curtis liked, and I go through it step by step there. The iPad app is free. If you got an iPad, get this, because this is usually $30. No, it's $29.99. They told me it's not $30. Sorry. And here's Math-Inspired, education.ti.com, one-stop shopping right here. And that website again, I have it somewhere. I'm sure I have it somewhere. on one of these things.
Tom, while you're looking for that, I do want to put a little plug in there. You've been doing a lot of work for us on that transformational geometry stuff. And so I just want to kind of give you a shout out on the transformational geometry videos that you've been doing on our YouTube channel. People can go there and check out those. And you don't have to have the Nspire software to follow along. You can just, watch the videos and do those activities without them. But if you do have the software, it is helpful, certainly. I did find a nice activity on trig ratios in the Math Inspired, and there's kind of a corresponding one, I think, on the 84 Activity Central as well. But there's a really nice one for trig ratios for in the geometry link. If we were talking about the trig ratios, if that was kind of the trigonometry that we were looking for, there's a nice one for that as well.
Yeah, is that in the geometry? That's in the geometry.
It is.
Yeah, right triangles. Yeah, that is a good one. I have seen that one. So, all right. So, so thanks, Curtis, for inviting me, and for those of you who attended, I hope you got something out of this. Feel free to email me. My email, I think, is on my website, the website created for you. But this is my email, and this is the website that will give you all this stuff, and I hope you can use it. And I wish you well as you adapt to these unusual times.
Hey, Tom.
Yes.
Before we jump off of here, let me share my screen one more time here. Sure. And I will, oops, I need to click share here. And I want to share that that trig ratios one just really quickly because
good.
You said it was a really nice one. So wanted to be sure to kind of pull that up and see if we could answer that question for our person who asked a little bit about these. So one thing that's really kind of cool about this one, we're just looking at the trig ratios, making the changes to sine, cosine, and tangent. What effects do those have on the value of the ratios? And all I'm really changing is the degree measure of this angle here. Same thing is going to be happening here, and you guys can see the color, as Tom mentioned earlier, the color corresponding pieces here. We've got this segment AC and this segment AB, corresponding lengths measures up there, and the ratio connected, and so you can kind of see those pieces happening. Students can really kind of play with the effect or the impact of changing that angle on each of those pieces, in particular the tangent here. Kind of a nice little one, but it's quick, it's fast, and students can see it really quickly. So I haven't seen any more questions roll in this evening. We've kind of done a sort of a shotgun blast of all kinds of different things you can do on TI-Nspire. I did notice that we had at least one or two people out there teaching geometry with the 84. And we do have a whole series of activities and things on 84 Activity Central. Some of them actually similar to what we just did here. So one question we just got was, is this for teachers or students? We're happy to have students get on and log into these live office hours anytime. We'd love to have students ask questions on here, teachers asking questions as well. We want to be able to share and help as much as we possibly can. And so we've had some students log into other office hours in the past, and they've gotten some of their questions answered. We may not always know everything that you want your students to know right away, or we may be giving them answers that they weren't supposed to get till tomorrow, but we are certainly happy to have students here and want to be able to help them and answer questions if they join. So
Yeah, and just to reiterate that, keep in mind the goal is to get to the students, not to the teachers. We want to make sure we
ultimately,
help the students. So that's why we field test all these things that we try out on students before we even take them to teachers. Because if they don't work for students, what's the point?
one other thing I guess we can do, and I can put a little plug here for your webinar that you just did earlier this week for Texas Instruments. You did a webinar for Earth Day
Yes.
just a little bit ago, and that was really kind of a cool one. You want to give a short plug for the recording that's going to be on the website?
Sure. In fact, I'll even put a link to that. I'll put a link to the recordings on the on my website. So if you're interested,
Oh yeah, that would be great.
I was really surprised how many people came for that one. Several hundred, which I was shocked, and the response was really kind of cool. But what it is plastic straws, of course, are a problem. And one of the questions is how many straws are used every day in the United States? And
Oh yeah.
according to Parade Magazine, it's 500 million straws per day.
What?
And so the questions that we ask and have the teachers, we actually had them solve it and have students solve it, is if you took those straws and put them tip to tip, how far would it go around the equator? Or how many would it go around the equator, or whatever? Or if you took in 1 year, how far would it go from the Earth to the moon? And so we do all that mathematics. Those are types of questions. But the one I like the best is if they were all plastic, and they aren't, but if they were, if we melted them down and made a box on top of a football field, like from goal line to goal line, sideline to sideline, how high up would that plastic be for 1 year of plastic straw? Just straws. Don't even talk about plastic bottles, because that's worse. But so anyway, those are the questions we answer. A lot of perimeter, area, volume, problem solving. Students have to ask for the information they need.
I got a question for you. I have no idea how deep that would be on the football field. Is it like, give me a scale? Is it feet, meters, miles?
So we did it in feet. Okay. And I'll give you the answer. I'm not going to ruin it for anybody, I'm sure. It's over 100 feet tall. So think of a block of plastic sitting on top of a football field, almost 10.5 feet high, or 100 feet, a little over 100 feet high, 10 stories.
That's something. That's something. Well, that sounds like an interesting.
That's from straws for 1 year. Just straws, not plastic bottles, not plastic anything else. And that's why when I go to the restaurant, I'll say, please, no straw. And the waitress, they try to be nice, and they'll give me a straw, and then they'll take it away and throw it away. And I'm like, no, you missed the point. I didn't want it originally. Now you're just throwing it away for whatever. So thanks for that plug. Thank you for that plug.
Yeah, I thought maybe you'd like to talk a little bit about that.
Yeah.
Well, it sounds like we've kind of got a good place here to wrap up. We've got some thank yous and people who enjoyed our time together. Tom, every time I get to talk to you, I really enjoy it, and I learned something. And so thank you very much for joining us this evening. And I just want to reiterate, as I did at the very beginning, that we hear you, and we want to do whatever we can to help. And so if there are questions that you have, things that you would want us to do one of these office hours around, I know we had somebody ask if this was for students. We'd love to, if there was a topic you want us to talk to your students about, we'd be happy to do something like that. Just, let us know what you guys are interested in, and put it in the chat box there, and we'll be monitoring that. Otherwise, I will go ahead and sign us off here for this evening. And we will see you guys on the next round.
Okay.
Good night.